Okay, here we are. Am I on the tape now? Am I here?
No. Yeah, no.
Now I am? Okay. What's the lighting like? Is it good lighting?
Yes.
Do I look handsome? Yeah. You can call me a lot of things. One of them is not handsome. Okay. All right, now. So what we're starting today is the periodic table. You've graduated from the blank periodic table to something that has symbols on it, etc. Now, let's look and see what we have here. In this particular periodic table, let's look at gold. Okay? You have the name gold. You have the symbol AU. Yeah? And you have 196.96569, which is really the atomic, we used to call it the atomic weight, although they've since gotten away from that because it's politically incorrect, scientifically politically. Because weight is actually, talks about gravity. Okay, you want to go that way? Thank you. You better? Okay, you'll survive. Excellent. Based on isotopic abundances, yes, percent isotopic abundances. What else is here? You have 19.3, which is the density, 19.3. Means nothing to you, does it? Yeah, Laura's over there. Sorry, nothing. Well, if you think it this way, the density of water is 1, so it's 19.3 times denser than water. Now it means something, right? It's very dense. Matter of fact, it's this whole area here, you have the densest. This is 19.3, 13.5, 21.45, 22.6, 22.6, 21.0, 19.3. So you can see that this whole area here is you get a lot of high density in here. Okay? So from right here it gets higher. This is even 13 hafnium. Down here is in the 7s, 8s, 9s, 9.84 lutetium. So you can see that they're very dense. Yeah. So what else does it have? It has the what? That's called the electron configuration. But look at this. It has 4F14, 5D10, 6S1. It's a little different from what we learned in terms of the Aufbau principle, but that's okay. It's still giving you the things there. Yeah. You'll see that the only S, see, this is going to be 5D9, right? Correct? Well, you'll see that in terms of stability, it's taking one of the S electrons away, right? Remember we talked about copper, the exception with copper. Remember how it goes from 4S2 3D9 to 4S1 3D10, and then 3D10 is lower energy, so it'd be 3D10, then 4S1. Well, same as here. This is going to be 6S1, 5D10, right? And it has some other things here, melting points, etc. Okay? Electron volts, etc. Okay, now. So, what we want to also look at, you not only want to look at what an element is and read off basic pieces of information, but what about that element relative to where it falls on the periodic table and what's around it? What's in the same row? What's in the same column? What's in the same section? So you can tell a lot about an element just by looking at where its location is, not by itself. This isn't the teenager's view of it. Teenagers do things, but they don't realize how their actions will affect the world around them. And that's okay, because that's the way, that's normal. But when you become older, hopefully you start to network and see how you respond and how the rest of the environment responds to you, how you respond to the environment and vice versa. So we want to look and see how it goes around. So we want to look a little bit at the periodic table. What are some early theories of the periodic table? We have, what are some early theories? Linda? Yes? Mr. Brooks? Yes? Anybody? Remember that's what you had? What were you doing? What were we doing? Are we working? Yeah, go ahead. What do we got?
No-brainer grouped elements in triads.
Dobrainer, I'm not sure, forgive me if I'm mispronouncing that. He grouped elements in triads, and those triads were based on similar what?
Properties.
What kind of properties? Physical and chemical properties, right? Yeah. And what else? Did he predate Mendeleev? Yes, he did. Do we have a year for him? 1817? Okay, 1817. So he was early. Well, what century was that?
17.
No, the other way. 19th century, early 19th century. Okay, who else? Anybody else? What about Newland? Did you run across Newland in your studies? What about Newland? Yeah, Linda. He classified 56 elements into 11 groups, right? So that's about 5 elements per group-ish, right? 56 elements into 11 groups, okay? And what were those groups based on? Similar physical properties. Very good. So these early pioneers, if we can do that, in terms of elements, everything's made of an element, everything. And these early scientists decided that let's learn about the elements by putting them in groups. We do that with learning information. It's called, I didn't know this word until I became a teacher, and they talk about it in teaching theory. It's called chunking. Anybody ever hear of chunking? When you take large bits of information and you learn that, instead of very small, minute pieces, you take chunks of information. Or instead of taking a big concept like a giant piece of paper, you chunk it. You take big pieces off, and you look at those individually, and you chunk it. It's called chunking. And they thought that, well, you know, if we put some of these elements together, that we might be able to identify more aspects of these elements, because there might be similarities among certain elements. And they give me probably the most famous group of elements where they're very, very similar. You know, it's the one thing, I would say, as a young chemistry student, it's the one group that you are most familiar with relative to having, that group having a unique characteristic. There's one very unique characteristic for this entire group of elements. What's that group? Anybody? Yeah. The noble gases. Very good. How many people agree with Linda, the noble gases? The hands are slowly coming up. Miss Miller's from Georgia. She's a little bit, she thinks very loudly. I can hear her think. She's also very tired. Long day, long week already? No? Okay. She looks like one of the great thinkers. If Rodin had a sculptor, a model in mind, it was Miss Miller, a great thinker. Okay, so what are some other columns? Let's talk about the noble gases before we get into Mendeleev. Tell me something about the noble gases. Who has noble gases? Oh, excellent. But before, Arbino, what were you going to say about noble gases? I said, tell me about noble gases, and you raised your hand.
They don't react.
What is it?
They don't react.
Yeah, probably the most important aspect of them is that they don't react. Is that true for the noble gases? I mean, is that a rule of thumb, or is it a hard, fast, cold, absolute rule? Let's go to the noble gas group, shall we? Captained by Miss Miller. Yes. What would you say about that? Is that a rule of thumb, or a hard, fast, absolute, cold, unrelenting rule? What would you say about that? Rule of thumb, yeah. I mean, I could tell you too, xenon difluoride, xenon tetrafluoride, xenon bonds with halogens, okay, under certain conditions. When we do molecular geometry, we'll look at some of those, okay, some of those compounds, yes. What else? Tell me something about noble gases. What have you found in your research?
Their S&P sublevels are...
Yeah, the S&P sublevels are filled. In other words, this is the 1s is filled, it doesn't have a P. The S&P, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, 5s2, 5s2, 5p6, 6s2, 6s6, etc. What else? Now remember, the valence electrons are going to be the S&P electrons, right? That's very important. Acknowledged? Baslan, do you understand that? What else? Sean, what do you got to contribute, Sean? You don't seem to be contributing much today.
Under standard conditions, they are odorless and colorless.
Under standard conditions, they are odorless and colorless. Okay, under standard conditions. What do you mean by under standard conditions? When might they not be colorless?
Like when they're put under extreme conditions.
When they're put under extreme conditions. Give me a very, very, very cool example of when that might be true, for at least one of them that I'm thinking of right away. Neon, yeah. You run electric current through neon, what color does it turn?
Yep. Green.
Look that up. Look up neon lights. Neon. What color is neon when you run an electric charge through it? What is the characteristic color of neon when you put it to a flame test or a electrical test, or you run extreme current through it? What do you got? What color is it? Anybody? I can tell you guys don't come from big cities. All right, we'll put that on hold for a minute. What else do we have? Ginny, you have anything on noble gases?
Sometimes they're called as inert gases.
Sometimes they're called the inert gases, and we can understand why, right? Yeah. What else? What is it?
Because they rarely take part in a reaction.
You got to say that again.
They're called as inert gases because they rarely take part in a reaction.
Yeah, they don't react chemically. That's right. Very good. Excellent. Anybody else have anything to contribute? Inert gases, we don't really have a lot to say about them because they don't really react. I tell you something that's interesting. When you think of a gas, you think of it rising, right? You fill a gas like a helium balloon, right? It's going to rise, right? Very rapidly, isn't it? I put xenon or radon in a balloon. It's going to drop like a brick. Weird, isn't it? Yeah. Why? Why does it do that? Because what's the average weight of air? Air is 80% nitrogen, which is N2, right? So that's 14 is 28. Oxygen is 32, 16, 16. Yes? So you say the average atomic weight of air is like 29-ish. You'd say 28 and 32, but it's 20% 32 and 80% 28. So let's say 29-ish. Is that all right? Whereas radon is 222. Xenon is 131. So it's heavier, isn't it? Because as we will learn, you ready? As we will learn. Put this in your brain. If I have the same number of particles of xenon and the same number of particles of air, right? If I have the same number of particles of air and xenon, normal conditions, or standard conditions, around zero, around right now, ish. Same number of particles of air, same number of particles of xenon. Same volume. Same volume. Same volume. Same volume. Right? So, the helium, same way. Same number of particles, same volume. Volume doesn't change. The mass changes, doesn't it? So, xenon, if you take a balloon filled with xenon versus a balloon filled with helium, same volume, same number of particles, the helium's going to float away, the xenon's going to drop like a rock. It's really kind of cool. What else? What do we have an answer to neon and electric charge? Yes.
Red.
Red. How do I know that? What's neon used in a lot?
Signs.
Neon signs, yeah. Neon signs are red. You could paint them blue, I guess, but different colors. But yeah, it's red. Neon signs. Clear glass tubes, electric charge going through it. You get red. Cool? Yeah. All right, what else? So let's talk about Mendeleev. Let's go back to Mendeleev. What year was did he publish his periodic table? Anybody? Yes. 1869. Post-American Civil War Reconstruction. Ulysses S. Grant was president in the United States. What was happening around the world? Anybody know anything about the history of their country? 1860s, 1870s? Anybody? What was going on? In Korea, what was going on? Anything? Do you know? A lot of Koreans in here. It's a little embarrassing. How about in the Arab world? Anything happening in the Arab world that we know of? Nothing was happening? Just hanging out? Were you just hanging out? What were we doing? Anything happening? Yes.
There was a rebellion against the Ottoman Empire.
There was a rebellion against the Ottoman Empire in the 1860s? 1870s?
Almost. No, after that.
Okay, I can deal with that. That's fine. Cool. Excellent. Somehow I think that rebellion was going on for a long time.
Yeah. Almost 60 years.
Yeah, a lot, yeah, hundreds of years I would say, but 1860s. Okay, I can buy that. Anything else going on? So the Arabs were revolting against the Ottomans. The Southerners in the early and mid 1860s in the United States were rebelling against the North. We had a rebellion in the United States. Anything else going on? Brazil, nothing? Nothing springs to mind? Okay. No? Where are you from, Eamon? Where? Anything happening in Malaysia? Okay, everything's all right. Excellent. All right. So what did Mendeleev do, Linda? I mean, Salama. What did Mendeleev do? What was his periodic table like?
He tried to find a way to show the relationships between the 60 elements.
He tried to show more relationships among the 60 elements. 3 or more is among, 2 is between, right? So among the 60 elements, he wanted to show more. And what was, when Mendeleev got through with it, what did he call it? His organization. He called it a what?
Periodic.
He called it a periodic table. He's the one that named it, really, didn't he? Yeah. And what did he organize the elements based on? What did he organize it?
Atomic mass.
Atomic mass. Atomic weight, he would call it, but atomic mass. And you can see that it's basically organized according to atomic mass. Are there times, though, where that doesn't work? Looks like it works pretty well. This wasn't there. Technetium was a hole. They had a lot of holes. He didn't have as many elements. But was there a time where where it wasn't organized according to atomic mass? Here's one. This goes 55.8, 58.9, 58.6. There was a drop, right? What else? Anything else? Why don't you look that up? Contradictions with atomic mass and periodic table organization. Somebody want to look that up? Laura, you want to do that for us? Excellent. What is the modern period? Let's go to the modern periodic table. Who's with modern periodic table? Yes, Arminda. What's the modern periodic table organized relative to?
Number of protons.
What is it?
Number of protons.
I can't hear you.
Number of protons. Atomic number.
The number of protons, or the atomic number. That's correct. So when I say, when it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So it's based on the number of protons, as opposed to the number of protons and neutrons. Actually, that doesn't work so well because of the number of neutrons and isotopic abundances, right? All right. What else about the modern periodic table? See, the modern periodic table, you had a lot more elements, didn't you? What about down here? These were in here, right? These were in here. You had to push these aside and you put these in. It's kind of funky looking. But that up until World War II, that's what it was. These were up in here. It was really weird looking. And we name element 106 after Glenn Seaborg. He's the fella who took this out of this and put him down here and made it a more compact table. More compact. Yes? Made it more compact. Easier to study. That was Glenn Seaborg. A few other things relative to atomic theory made it easier. What else about the modern periodic table?
It was invented in 1920.
It was invented when? 1930? Excellent. 19 what? 1913, the modern periodic table. Excellent. I'm having a problem with accents today. It's okay. Excellent. It's not you, it's me. You speak normal, I don't. Okay, what is true English? Very interesting question. Okay, so, what else? Anyone else? Did you have an answer to that?
What was the question?
The question was, what are the contradictions? Where, when you organize the elements according to atomic number, where are there are decreases in the atomic weight, atomic mass, as you go through the periodic table? Where does that happen? Laura needs some help. Armindo, do you know?
Iodine is
Iodine over here? Yeah. Tellurium, look at this. 121, 127, 126. This is 121.7, 127.6, 126.9. Very good. Excellent. Anywhere else? Here, manganese and, iron and cobalt. Any others? Why are these in parentheses? Like these. See how they have parentheses? Why are they in parentheses? What do the parentheses mean?
Is that like they haven't been found like naturally or something like that?
Yeah, they haven't been found naturally. Okay. Well, why haven't they been found naturally? Any idea, maybe? Because they're so unstable, really. They're so unstable. The ones with, see, these are mass numbers. These are mass numbers. You know, remember we studied isotopes? An isotope is a variation of an element based on a number of neutrons. And the mass number of the dominant isotope, generally, you can round it to the nearest whole number, and that's generally the most stable isotope within reason, right? For instance, cobalt would be 59, nickel 59. So you have exceptions maybe through the table, but generally we say that. When we do calculations, we round to the nearest whole number. It just makes it easier, you know. But this is a mass number of the most stable isotope. This is the one that they actually isolated, generally. I mean, I would have to really go through the literature, and because I haven't taken a serious chemistry course in many years. I haven't even read a journal in many years. I'm too busy with my grandchildren. But I would doubt that, you know, with borium 270, that isotope, that there's more than one isotope that they have found. I would find it hard to believe. I mean, they may have found it for like, I don't know, you know, americium maybe, because it's, you know, one of the earlier ones. When I was in school, I remember distinctly (103) Lawrencium. That was it. Went to Lawrencium. Yeah. Okay, we're going to quit. So that's Intro to Periodic Table Part 1. It's 11 o'clock. I got 10 minutes. I want to go over the lab that you've got to start at home. You're going to come in and work on it, okay? All right, so that's Intro to Periodic Table Part 1. Stay tuned. We're going to do this with both sections. Well, I have 3 sections, so this will be a major part of it. Yes? Excellent. Okay, we're on. So periodic table part 1.